Good morning. Welcome to Turbo Machine classes. I am Professor V. Sushant Kumar, Department of Mechanical Engineering, Angadi Institute of Technology and Management, Belagavi. So today we'll start with our first video lecture. This subject has been divided into 5 modules. So first I will brief you all about all the 5 modules. Then we will start with the introduction part. So module number 1, it is divided into 2 sections, introduction, and second section is thermodynamics of fluid flow. So in today's classes we'll start with the introduction, and before that I'll just read out, will explain you the topics that we are going to cover. So in introduction we have definition of turbo machine, parts of turbo machines, and comparison between a positive displacement machines and a turbo machine, and the classifications. And in the second class we will be covering about dimensionless parameters and the significance, unit and specific quantities, model studies, and a few examples. And this dimensionless parameters, we have already studied this in our previous semester in fluid mechanics classes. So we'll be just using that concept in understanding unit and specific quantities. And in the second part of this module we have a thermodynamics of fluid flow, so wherein we'll be studying the application of first and second law of thermodynamics to the turbo machines. So already we know first and second law of thermodynamics, so how it is applicable to the turbo machines, that concept we'll be studying here. And along with that we'll also be studying two new terms. They are static and stagnation properties. So all these days, all these semesters, you have studied only properties, but actually there are two types in that. One is a static property and second one is a stagnation property. So we'll be studying the distinction between them, and which one to use in which context, all that will be seeing. Module number 2 is again divided into two sections. First section is of energy exchange in turbo machine, and second section is general analysis of turbo machines. In energy exchange of turbo machines, we'll be studying about Euler's turbine equation, alternate form of Euler's turbine equation, and velocity triangles for different values of degrees of reaction. So this part is very important because as we are going to study the velocity triangles here and few important derivations, this module is very important in understanding the subject. And in the second section, general analysis of turbo machine, so it gives you information about the whole turbo machines. Okay, all the velocities triangles of different turbo machines and degrees of reaction and effect of blade discharge angle on performance, general analysis of axial flow pumps, compressors, degree of reaction, velocity triangles. Means it gives you the overall information about various turbo machines. Module 3 is about steam turbines, classification of steam turbines. Basically we are going to study impulse turbine and reaction turbine in this, and stages and methods of compounding, and we are going to solve few numerical examples. And this module is interesting because here we are going to solve the problems using analytically as well as drawing the vectors, taking the scale and drawing the vectors. So whichever method you people are comfortable, you can follow that method in the examination. Module 4 is all about the hydraulic turbines. So basically we have three types: Pelton wheel, Francis turbine, and Kaplan and propeller turbines. So for all the three types of turbines we'll be studying the velocity triangles, and for all the three types of turbines we'll be solving the numerical examples. And even this module is interesting, so probably after the first module we'll directly go to module number 4 and we'll finish this. So first we'll discuss module 1 and module 2 half section, then we'll go to the module 4. Module number 5 and last module, it's about centrifugal pumps and centrifugal compressors. So even here we'll be studying about velocity triangles and what is the head, what is the relationship between capacity and head, minimum speed for starting the flow, maximum section lifts, okay, and net positive section head. And in the compressors we'll be studying about stage velocity triangles, slip factors, power input factors. So one thing we need to remember here is, so the velocity triangles that are going to study for the pumps, sorry, the velocity triangles that are going to study for the turbines will be entirely opposite when you are studying it for the pumps. Okay, so we'll see that as and when we come to these topics. Let us know how the question paper pattern would be in the main examination. The question paper will have 10 full questions carrying equal marks. So each question carries 20 marks. There will be 2 full questions for each module, and each full question will have sub questions. At the maximum we can have 4 sub questions. Students will have to answer 5 full questions, selecting 1 full question from each module. These are the textbooks and reference books prescribed by the university. In our classes, all the topics, so I'm going to refer the first textbook, that is Introduction to Energy Conversion, Volume 3 by B. Kadambia and Manohar Prasad. So this is a standard book. So all my lectures contains references from this textbook. Before proceeding with the first module, we need to know some basic definitions that already we have studied in our lower classes. So the first one is pressure. So already we know this pressure term and we have studied in detail about this in the previous semester. So here I am just going to brush up the basic definitions. Okay, so pressure always acts inward. Okay, so means pressure is synonym to the stress. Okay, we have come across stress word in strength of materials. So when we are considering the solid body, so we talk about the term stress, but when we are dealing with the fluids, we use the pressure term. So both have the same unit. The standard atmospheric pressure is 101.3 kilopascal or 0.1013 megapascal, or it is also it is, we can also write in terms of 1.013 bar, or it is 14.69 psi. Psi refers to pounds per square inch. Second definition is pressure head. In fluid mechanics, head refers to energy per unit weight or mass. Okay, so here this is the Bernoulli's equation, P by rho g plus V square by 2g plus z is equal to constant. Okay, so this is pressure per unit weight. Okay, this rho g, it is refers to weight, and V square by 2g is velocity head. Okay, this is P by rho g is pressure head and this is velocity head. Okay, and this is data head. Okay, so now this P by rho g, okay, if you simplify the unit, okay, you will get the unit as meter. Okay, even if you simplify this V square by 2g, you will get the unit as meter. Okay, so the pressure head is nothing but P by rho g and its unit is meter. A third definition is momentum. Momentum is the product of mass and velocity of an object. It is a vector quantity. It has both magnitude and direction. If the mass is in kilogram and velocity is in meters, then the unit of momentum is kg meters per second. So we need all these three definitions to understand the definition of the turbo machine. Okay, in the next section we'll start with the definition of the turbo machine and other related topics. Okay, let's start with the definition of turbo machine. A turbo machine is a device in which energy transfer occurs between a flowing fluid and rotating element due to dynamic action. This results in change of pressure and momentum of the. So in this definition, you need to remember the energy action takes place between flowing fluid, okay, and rotating element. Okay, there is an energy exchange, either it is from the fluid to the rotating element or from the rotating element to the fluid, based on which type of a turbo machine it is. And how it is taking place, it is due to dynamic action. Okay, so when the energy action takes place between the flowing fluid and the rotating element due to dynamic action, what properties are going to change? There is a change in pressure and momentum of the fluid. So this is the generalized definition of the turbo machine. If you refer different textbooks, they give different definitions, and most acceptable definition is what you are reading now. Okay, so I'll just repeat. A turbo machine is a device in which energy transfer occurs between a flowing fluid and a rotating element due to dynamic action. This results in change of pressure and momentum of the fluid. The components of turbo machines: rotating element, stationary elements, shaft, housing. So you can see from the sketch, this is the shaft. Okay, so on this shaft we have rotating blades and stationary blades. So you can see from the sketch, okay, we have stationary blades as well as rotating blades, and this is the inlet. Okay, so the fluid enters and it passes between the blades, stationary and rotating blades, and it comes out. So when it is passing over, I am considering the example of turbine. Okay, so when it is passing over, energy exchange takes place between the from the fluid to the blades, and blades are connected to the shaft, and in turn the shaft is connected to the generator. Apart from this, we have casing, the outer cover. It's not compulsory that all the turbo machines should have the casing. For example, if you consider the ceiling fan, it doesn't have the casing, so it depends on the purpose and design. Okay, so we'll discuss about that later. Okay. So in the rotating element, we have vane, impeller, blades. Okay, and in the stationary elements, which usually guide the fluid in proper direction for efficient energy conversion process. The function of stationary blades, they guide the fluid. And next is the shaft. This either gives the input power or takes out the power depending on what type of turbo machine we are using. And the next one is housing. So it keeps various rotating, stationary and other passages safely under dynamic conditions of the fluid flow. For example, if you consider steam turbine parts and Pelton turbine parts, the outer casing cover. Okay, next topic is classification of turbo machines. So we have various ways of classifying the turbo machines. So the first one is based on the energy transfer. So based on the energy transfer, either we can have power generating turbo machine and power absorbing turbo machine. So what is power generating turbo machine? If the energy from the fluid is transferred to the impeller or blades, then wherein we are generating the power, then that kind of turbo machine we call it as power generating turbo machine. In power absorbing turbo machine, energy is transferred from the blades to the fluid, unlike our compressor, pumps. So that type of turbo machine we call them as power absorbing turbo machines. Next, second one is based on the fluid flowing in the turbo machines. So we have different turbo machines handling different types of fluids. Okay, for example, water, air, steam, hot gases, liquids like petrol. Okay, so even we have classification of turbo machines based on the types of fluid they handle. So in the previous slides, we have seen the classification of turbo machines. So I just given this picture so that you can easily understand different turbo machines. So turbo machines can be classified as rotodynamic turbo machines, positive displacement turbo machines, and other types of turbo machines. Okay, this rotodynamic turbo machine can be further classified into two types. So that is energy, fluid energy to mechanical energy, means energy transfer is taking place from the fluid to the shaft, blades and shaft. Okay, and in the second case, mechanical energy to the fluid energy, means energy transfer takes place from the shaft to the fluid. Okay, in the first case, examples are a turbine. Okay, we have steam turbine, gas turbine, water turbine, and in the second case, where energy transfer takes place from the shaft to the fluid, we have pumps, fans, compressors, blowers. So all these pumps, fan, compressor, blowers, okay, so they take energy. So we are supplying electrical energy. That electrical energy is converted into mechanical energy, the shaft, and that mechanical energy is further transferred to the fluid. Okay, for example, if you take fan, ceiling fan, okay, we are supplying electrical energy, and that energy is transferred to the blades, and further from the blades it is transferred to the air. Okay, so in the positive displacement machine, okay, we have again different types: pumps, motors and jacks. Okay, the pumps are classified again into rotary type, reciprocating type. So in rotary type of positive displacement machine, we have gear pump, screw pump, vane pump, lobe pumps. Okay, and in reciprocating type, we have diaphragm pumps and reciprocating pumps. Okay, and in other types of turbo machines, we have other examples like hydraulic brakes, jet pumps, airlift pumps, thermosiphon pumps, air brakes, hydraulic ram. Okay, okay, let's come down to the rotodynamic. So I told you rotodynamic turbo machines are divided into two types. One is the power generating turbo machine, and second one is power absorbing turbo machine. Power generating turbo machine example is a turbine. We have a steam turbine, gas turbine, water turbine, and this is further classified into based on the flow: tangential flow, axial flow, radial flow, mixed flow. So example of tangential flow is Pelton wheel turbine, example of axial flow is Kaplan turbine, and example of radial flow is Francis turbine, and example of mixed flow is modern Francis turbine. And even these power absorbing turbo machines can be classified into axial type, radial type, mixed type. So this is the overall classification of the turbo machines. Next, comparison between positive displacement machine and a turbo machine, important from the examination point of view. Most of the time they have asked these questions in the examination. So the first, okay, in the first column we have positive displacement machine, and in the second column turbo machine. So first one is based on the action. Okay, under the positive displacement machine, it creates thermodynamic and mechanical action between moving members and static fluid. Energy transfer takes place with displacement of fluid. And in turbo machine, it creates thermodynamic and dynamic action between the rotating element and flowing fluid. Energy transfer takes place if pressure and momentum changes. And the second classification is based on the operation. So positive displacement machine, it involves unsteady flow of fluid and reciprocating motion. So positive displacement machine we have reciprocating motion, okay, and in turbo machine we have rotary motion. Okay, very important, we should this is the major distinction. Okay, positive displacement machine we have reciprocating motion, and in turbo machine it involves steady flow of fluid and rotating motion. This is very important. Okay, in turbo machine we have rotating motion, and in positive displacement machine we have reciprocating motion. And the third classification is based on mechanical features. In positive displacement machine, because of reciprocating masses, okay, vibrations are more. Okay, since we have reciprocating motion in positive displacement machine, the vibrations are more, and hence low speeds are adopted. Okay, and we require heavy foundation to install the positive displacement machine, and here the mechanical design is complex because it involves valves and other moving parts. Under the turbo machine, okay, rotating masses can be completely balanced, okay, and vibrations are eliminated. Means as compared to positive displacement machine, the vibrations in turbo machines are less and we can attain high speeds. Okay, and next second one is we can have light foundation. Okay, as the vibrations are less, the foundation can be light as compared to positive displacement machine, and as compared to positive displacement machine we can have simple design. Next, fourth difference is based on efficiency of a conversion. Under positive displacement machine it has high efficiency, okay, because of static energy transfer, and efficiency of compression and expansion process are almost same. Okay, next under the turbo machine efficiency is low as compared to positive displacement machine, okay, because of dynamic action, and efficiency of compression process is low. And fifth difference is based on volumetric efficiency. So based on volumetric efficiency, under the positive displacement machine, okay, it is much below that of a turbo machine. Means volumetric efficiency of positive displacement machine is less than the turbo machine, and low fluid handling capacity per unit weight of machine. Okay, under the turbo machine volumetric efficiency is almost 100%, and high fluid handling capacity per unit weight of the machine. And the last classification is phase change and surging. In case of positive displacement machine there is no change of surging or phase change, okay, but under the turbo machine it causes a cavitation. Okay, so what is cavitation we have discussed already in fluid mechanics. Next, it erodes the steam turbine blades. Okay, if it is a steam turbine blades, it erodes the steam turbine blades, and surging leads to unstable flow, and it causes vibration and may destroy the machine. So these are the classifications, comparison between positive displacement machine and the turbo machine. So topics discussed in today's class. So we discussed about the syllabus, what are the topics that are there in the turbo machine subject, and we discussed basic definitions like what is pressure, pressure head, momentum, and later we discussed the definition of turbo machine and the classification of turbo machines. So how the turbo machines are classified based on different categories, and difference between positive displacement machine and a turbo machine. Okay, so in the next class we will discuss about dimensionless parameters and specific quantities, units and specific quantities. Okay, then we will go for few examples. So this is the end of the class. Thank you.